Okay, so we will be talking about the multiple degrees of freedom systems, which are more than 1 degree of freedom. 2 degrees of freedom is a special case of that, and we covered that. Now we will be doing it in the more general context, solving an eigenvalue problem and interpreting the eigenvalues and eigenvectors, and also normalizing the eigenvalues and eigenvectors. Now we will be dealing with first undamped systems, which are forced or unforced. In any case, we have to start from assuming a harmonic solution and substituting that into our equations of motion. So we have an undamped system with a mass stiffness matrices. So if you substitute that harmonic solution to your equations, you are going to get a so-called generalized eigenvalue problem in the form of a matrix times a vector is equal to 0. And this kind of equations have a solution only if the coefficient matrix is singular, which means that only if the rows or columns of that matrix are dependent on each other, which means that the determinant of the coefficient matrix, which is frequency dependent, omega contains omega terms in it, the determinant has to be 0, and this gives us the characteristic equation from which we solve for the eigenvalues or the natural frequencies, so to say. The problem we have here, let me show it here. This problem we have here, k minus omega I squared m times ui, is called the generalized eigenvalue problem. The normal eigenvalue problem, if you remember, is this one. Lambda I minus a times a vector is equal to u, or lambda u is equal to au is the regular eigenvalue problem. But the generalized eigenvalue problem, which we have here, can be converted to the normal one as follows. You just multiply your problem with M inverse, mass inverse. Since mass matrix is always invertible, it is possible to do that. And once you do that, you get an M inverse times K here, which you call A. Then you get a M times M inverse is an identity matrix. So eventually you get lambda I minus A times U is equal to 0. So this gives you the eigenvalue, regular eigenvalue problem, for which you can solve for the eigenvalue, which is the natural frequency squared, this one. Taking the square root of that gives you the natural frequency and the corresponding mode shape ui. You can get the corresponding mode shape from solving the eigenvalue problem. Now, the eigenvalue problems to a certain size can be solved by hand, but after that you need a computer solution. I guess this is more or less the limit. For example, let's say that we have a 3 degree of freedom system, 3 masses, 4 springs, and let's say that for simplicity, all the springs are the same, all the masses are the same, masses are M, springs are K, okay? In which case, the stiffness matrix, the matrix K, is going to be made up of a symmetric matrix of a certain structure. All the diagonal elements are 2K. Off diagonals are K, minus K, I'm sorry. And there is no connection between the first and the third mass matrix. So the stiffness between them is 0 coefficients. The mass matrix is a diagonal one, which is a simple thing. So we find we write the problem. To determine the eigenvalue problem, we first write this determinant of k minus omega squared m, which is the determinant of this matrix, which can be found. 3 by 3 matrices are okay to a certain extent. You equate that to 0 and you get an equation of third order in terms of lambda, which can be solved. But anything higher than third order cannot really be solved. So you have to resort to computer solution. For example, even the generalized eigenvalue problem can be solved with MATLAB. In MATLAB, for example, if you have the K and M matrices, you just use this command, the I command. Well, here V is the eigenvectors, mode shapes. D is the diagonal matrix with diagonal elements as the eigenvalues. Okay. So if you solve your equations, if you solve the eigenvalue problem, what you are going to get from MATLAB, will be the following. Obviously, in MATLAB, you cannot have K's and M's. You have to substitute something for them. For example, you can substitute 1 for both of them. So the first natural frequency will be, first eigenvalue will be 2 minus root 2k over m. The second one will be 2 root k over m. The third one will be 2 plus root 2k over m. After which, you can solve for the mode shapes, and mode shapes, as you know, have certain coefficients in front of them. These are arbitrary, okay? But the mode shapes are clear. There is a proof drawing of mine of the mode shapes. As you remember here, there are walls between the masses. So these things represent the walls. So you have 0.5 here, 0.7, 0.5, and 0 in the displacements. This is the first mode shape, which means that the maximum motion happens in the middle mass. The others move together, but with lesser amplitudes. In the second mode, the middle mass does not move at all, and the first and third masses move like in opposite directions. And in the third mode, the middle mass moves the most, and the first and third masses move together, but in opposite direction to the middle mass. Okay, so these are the mode shapes. A regular motion of this system will be usually a combination of all of these modes. And also note that these pictures look a little bit like the sine waves actually, and that is not coincidental. For example, this one looks like this sine wave, half sine wave. This one looks like a full sine wave, like this. And this one looks like a 1.5 sine wave, like this one, if you like. Okay? And there is a reason for that. If you increase the number of masses in this equation, like if you have like 10 masses, 20 masses, even more, actually these pictures you have of the mode shapes are going to look more and more like the sine waves, and that is not very coincidental. Okay. Another thing you should note that these are the mode shapes. If you multiply these mode shapes with each other, you are going to get zeros, which means that they are orthogonal to each other, and we will come to that later on. So that's one example of eigenvalues and eigenvectors, natural frequencies and mode shapes of a third order system. Now we will talk about a little bit about the unrestrained systems. Remember that we called them the semi-definite systems before, in the context of 2 degree of freedom systems. It's the same thing. These systems are not attached to a stationary frame. They are not connected to a wall. So those systems have a rigid body mode. For example, if you have moving railway cars connected with springs to each other, such a system is unrestrained, and it definitely will have a rigid body mode. Okay? And the rigid body mode is going to be defined by this q double dot plus omega squared q equals 0. That is the vibrational mode motion. And as you know, since the rigid body mode has a zero frequency, since omega is 0, q double dot of t will be 0. And if you integrate this twice, you will get q of t will be alpha plus beta t. This will be the rigid body motion. So all the masses will move together without any vibration. Okay, alpha and beta are constants to be determined from the initial conditions. Now, one of the modes of such a system that you obtain from the eigenvalue problem is the rigid body mode, which we will call U0. Let's call it U0. And the omega 0 corresponding to that will be a 0. Here, omega 0 will be 0 corresponding to the rigid body mode, okay? But what you see is when you have the omega 0, 0, you have k times U0 is 0, which requires that the determinant of the stiffness matrix to be 0. And when that happens, actually, the mode shape you obtain for this system, for an unrestrained system, has to be that all the modes move together as if the system were a rigid body. So the vector, the eigenvector, is going to be made up of all ones. The mode shape is going to be made up of all ones. Okay, for example, again, a simple example, the system with 3 masses, 2 springs, unrestrained, unconnected to anything. If you find the mass and stiffness matrices, this will be the stiffness matrix, this will be the mass matrix, and the eigenvalue problem will be obtained from this characteristic equation, from which you can solve for the eigenvalues and eigenvectors, okay? So, as expected, the first eigenvalue is going to be 1. Sorry, the first eigenvalue is going to be 0, okay? The second eigenvalue will be k over m. The third eigenvalue is 3k over m. And the corresponding mode shapes, this is the rigid body mode. Or this one is the rigid body mode. These two are the vibrational modes of motion, okay? So as you see, these are the mode shapes. And remember that, again, these are orthogonal to each other, meaning that their multiplication with one with the other one gives you a 0, because the mode shapes are orthogonal. At least in this context, we will see how the orthogonality works in the vibrational systems. Okay, so much for this part.